Buenas noches a todos los socios. La Asociación Mexicana de Geofísicos de Exploración les da la bienvenida a esta charla magistral del mes de julio. En esta ocasión tenemos como invitados a Sissy Tyson y James Corey Morgan, que nos hablarán de una charla muy especial y muy interesante, titulada Advanced Imaging is the World Solution. Antes de iniciar la charla, vamos a dar lectura a su semblanza de trayectoria profesional. Bueno, empezamos con Sissy Tyson, presidenta de Land Seismic Noise Specialist. Sissy tiene más de 25 años de experiencia en la industria. Comenzó su carrera en Western Geophysical en 1996 como geofísica de procesamiento de datos, después de graduarse con una licenciatura en Geología y Geofísica de la Universidad de Ciencia y Tecnología de Missouri. A lo largo de su carrera se ha desempeñado en varios roles de gestión e imagen sísmica, desde trabajar como procesadora a bordo en barco en adquisición sísmica en alta mar para PGS en Brasil, Nigeria y Canadá, hasta la gestión de atención al cliente para lo que en la parte del software, en la parte de imagen de tiempo y profundidad para Paradigm. Y más recientemente asumió funciones gerenciales en Ion y NEOS como director de procesamiento en tierra y vicepresidente de imagen sísmica. En 2017, Sisi se convirtió en socio comercial de Christopher Stork y comenzaron a construir a Land Seismic Noise Specialist en los líderes tecnológicos que son hoy. Welcome, Sisi, Alonso.
Gracias, Juan José. Yo les voy a leer la biografía de Corey Morgan, quien es director de servicios de yacimiento. Se une a LSNS con casi 25 años en la industria del petróleo y gas, iniciando como geofísico de campo con PGS, trabajando como procesador de QC en brigadas tanto marinas como terrestres alrededor del mundo. El inicio de su carrera tuvo una variedad de roles en PGS, Core Lab, GDC y Fugro JSON. Los últimos 15 años trabajó en compañías de exploración y producción, incluyendo Noble Energy, donde tuvo un rol clave en descubrimientos mediterráneos, BHP Billiton, Lukoil y Anglo Dutch Energy. Su trabajo ha incluido roles gerenciales y técnicos en adquisición de datos y procesamiento, interpretación cuantitativa y física de rocas, generación de prospectos y desarrollo de software. Señor Morgan posee un BSc y MSc en física por parte de Texas A&M y un grado adicional por la Universidad de Houston y Texas A&M en Kingsville. So we would like to welcome you both, and we leave it to you, Sisi. Please start the talk. Thank you.
Gracias, Juan and Alonso, and gracias por la oportunidad de presentar hoy. I will go ahead and share my screen. So can you see my screen now?
Yes, we can see.
Thank you. So the title of our talk is Advanced Imaging. Is it the whole solution? Our motivation for doing this talk was driven by the fact that we're hearing a lot about FWI and other advanced imaging techniques and how this is going to fix the problems with seismic data and make processing somewhat obsolete. So we kind of wondered if we could dig a little deeper into how close are we to having that actually happen. So in this talk, we're gonna talk about the findings from the SEAM2 Barrett 3D model data. And then we're going to go into the Teapot Dome 3D case study, and we'll talk about the processing and comparative QI that we did on that. And then we'll talk a little bit about some conclusions we drew from these two work on these two projects. So a little background on the SEAM2 Barrett model. This model was created by SEG to simulate unconventional hydrocarbon reservoirs. And specifically, it was meant to resemble the Eagleford Shale that's South Texas and does extend into Mexico. So Oxy published a paper in 2020 And the main conclusions in that paper were that there were no signs of the geobodies that were included in the model in the AVAZ volumes they produced, and that the main correlation of the AVAZ volumes produced was with the near surface, and that the PSDM that they did not correct the surface effects. So you can go onto the SCG library and take a look at that talk if you're interested. This is the link. So after that, Land Seismic decided to work on those data, and we later published. And what we showed was that while the geobodies still didn't show up very well in our AVAZ volumes, the volumes didn't correlate with the near surface after processing, and that removing the near surface effects was crucial for getting those attributes. So some images from the original processing and imaging from the Oxy paper. This is the AVAZ anisotropy. This is the azimuth volume, and it has the geobodies overlain here. These are the geobodies, and you can see there's a little not fully opaque outline of these on here. And then there's the white dots that correlate to this near surface depth slice, showing the acoustic impedance and showing that the correlation in their azimuth volume is primarily similar to the acoustic impedance volume. So these are some images from our processing, or an image from our processing. This is our AVAZ azimuth volume. Now, if you squint hard enough and maybe, I don't know, have a creative mindset, I don't know, have a strong drink before you take a look, maybe you could imagine that you could see some of these geobodies in here, but really it's a stretch. They are not obvious. But what you do see quite obviously are some faulting and other features that don't correlate to the acoustic impedance depth slice. These are, data driven, not driven by the velocities in the near surface. Now, so what did we do differently? Why are our volumes so different from the previous volumes? Well, what we did, we spent a lot of time on time processing, doing all the typical steps that you'd want to do before going into PSDM, like refraction statics, residual statics, surface consistent amplitude corrections, and we also did FWC, which is our proprietary scattering correction that attempts to correct for some of the near surface scattering from slow velocities over short distances in the near surface. So we did that, and the other thing we did was we decimated the heck out of these data. The model data set was 55 billion traces, and for a test, it just wasn't feasible for us to use that many traces. So we actually cut it down to 65 million, which is like 100th of the original traces. But interestingly enough, it actually produced a better result. So kind of interesting. Okay, so these are some maps from the surface correction processes that we did. So we've got refraction statics, surface consistent amplitude corrections. This is the source refraction statics, the receiver refraction statics, source amplitude corrections, and receiver amplitude corrections. These are the phase corrections from our FWC process. So our FWC process does a phase and amplitude correction. to correct for the near surface distortion. And you can see this is the source distortion and the receiver distortion. This is maybe plus 20 to minus 20 degrees, and maybe a little bigger on the receiver, plus 40 to minus 50 or so. And then you can see next to it, this is the S velocity at 30 meters from the model. And I'm going to go back and forth a few times to look at the source and receiver refraction statistics, the source and receiver amplitude corrections, just so you can see in relation to each other that all of these corrections mimic the near surface velocities. Essentially, every surface correction here is making that correction for the near surface velocity issues that are in this model. So, you know, the patterns are pretty plain in all of them, matching the velocity model. Maybe the receiver distortion from FWC is the least correlating, but it still is pretty obvious. So based on what we saw in the scene2 data set, we drew some conclusions. And those were that the surface effects are significant for seismic attributes. PSDM alone did not fix those surface effects. Massive data in the first processing did not fix the surface effects. But the careful time processing using you know, all the typical corrections plus our proprietary corrections, refraction statics, residual statics, surface consistent amplitudes, and then FWC, they all contributed to reducing the effects of those near surface and getting a AVAZ volume that didn't just mimic the near surface. Now I'll go into the teapot dome portion of the discussion. Teapot Dome dataset was acquired in 2001. It's from Wyoming in the United States. And it's provided as public domain data from the US Department of Energy and the Rocky Mountain Oilfield Test Center. So this dataset is readily available, and lots of people have run various tests and used it for various publications over the years. The Teapot Dome field was originally part of the US Naval Reserve, and it was part of this big bribery and corruption scandal in the US in the 1920s. So just for fun, I've included a bunch of cartoons, political cartoons from that era, just throughout the presentation, just so, you know, they're interesting and sometimes kind of funny. As far as Teapot Dome goes, production has mostly ceased there, but about 20 million barrels of oil and 52 BCF of gas were produced there over its lifetime. So, you know, pretty significant area. This is just the survey overview. You can see the CDP elevations. These are in feet. So it's about 4,900 to 5,600 feet. The fold map goes from 0 to 60. 60 is the max fold here in the middle. You know, not super modern high fold shooting, but it's not terrible. It's good enough that our proprietary processes that need significant statistics to work well still worked pretty well. And this is just the source and receiver map. So just a little, to give you a little background on what we were looking at here. This is our generalized processing workflow. I've highlighted our proprietary processes in red, including the wave equation refraction statics, machine learning denoise, 5D spectral editing, and the full waveform correction, or FWC as we call it. With those exceptions, it's a